Hey guys, we're running a little late today, and now we're good to get started. Respect. Most critical question is this: you still have it? What do you still have it? Can do attitude. Can do. Today is gonna be the first real test whether or not you're gonna have a can do attitude after today's lecture. Remember, I said that this class is progressively more difficult. The level of difficulty increased progressively. There are a few mountains we need to climb up. Today is the first summit. It's not going to be the main hill, or let's say the main mountain of this class, but it's going to be something that is going to be hard to deal with. Something that's going to be called as the Jacobian matrix. Jacobian matrix is related to constraints. Here's the deal. So what we know so far, so we know the kinematics. So we know how to describe a particle. And we know this. The particle is not what you can find in a real life, but it's a small mathematical thing. It's a small dot. And because it's so small, it's not having any rotational degrees of freedom. So when I'm saying that rotation of the particle, that's not existing. That's in Santa Claus. So what we can do with these particles, we can know their position with respect to any given coordinate system. What we're really interested is that we wanted to know the particle with respect to reference coordinate system, often called as a global coordinate system. We do this with help of body reference coordinate system that is translating and rotating together with the body. We also know that in this kinematical description, variables are components that are telling our kinematics. And once we're using this body reference coordinate system, then we need to know where this body reference coordinate system is located with respect to our reference coordinate system. This is going to be described by vector r. And then we also need to know how is the orientation of the body reference coordinate system with respect to reference coordinate system. That's going to be described by using angle theta. That makes a total of 3 coordinates. Rx, which is a projection of this R vector with respect to global x, Ry, which is a projection of the R vector with respect to global y coordinate axis, and angle theta. So everybody needs 3 generalized coordinates. Everybody needs 3 generalized coordinates. Okay, now what we're going to do today, or also what we learned. Sorry, I almost forget the one more thing, one more important piece of information that you are already familiar with. You know what's the concept of constraints. Not fully understand it yet, but you know at least a little bit. It's something that limits the motion possibilities between the neighboring bodies. And a week ago, we learned that there is a revolute joint where you're actually attaching 2 bodies together such that they are no longer able to separate from the point where the revolute joint is located at. So if say that I have body pen and body stick here, and I'm going to attach the revolute joint between these 2 bodies, this point will be common, regardless what's going to happen. Joints, they have the ultimate force, power, however you wanted to put it. It means that they cannot separate it anymore, regardless of the amount of force. You know that this happens in real life, that if you've got a lot of big force, like this, I can separate the revolute joint. It can happen in a real life. When we do the simulation, that's not the case. They cannot separate it. They are always something we can obey. So they are not going to be joints that are going to be breaking because of the forces. That's something we are not touching this class. Okay. Now I said that the concept that's going to make you confused is a Jacobian matrix because it's going to be mathematically quite involving. Meaning that we know how are the constraints. We know that. So we can make a vector of constraints. So we can put all the constraints in a one vector representation. Then we know what are the generalized coordinates. That's another vector representation. Jacobian matrix is something that we're going to do a partial operation such that we're going to differentiate these constraints with respect to generalized coordinates. The partial operation with respect to two vectors is going to give us matrix. That's what we're going to learn today. And then we're going to learn, if we're going to happy today. I think that I was a little bit premature when I mentioned that we might be able to run the kinematic analysis today. I'm not sure if we're able to do that today because this concept of Jacobian matrix constraint and so on and so forth, going to take a while to learn it in details. But if we're able to run the kinematic analysis, it's going to be the first analysis in this class. Like I promise, I'm saying that more than 50% of you are going to cry because of the happiness, not because it's so difficult, but it's going to be, oh my God, really? Did I make that happen? Yes, we all that make it happen. So that's our target, make you guys cry. How that sounds? You have a napkin with you? Okay, all right. But first thing first, what is that we discussed a week ago? Now, one more time, this kinematics. But kinematics is so important because the only thing we need to do, once we set down our mind about kinematics, the only thing we need to do is to be consistent in terms of kinematic analysis, in terms of constraints, in terms of dynamics. Dynamics actually is nothing but following the kinematics, nothing but following the kinematics. So really the only decision we need to do is to figure out how we do the kinematics. And there are many ways to make it happen. But commonly in multi-body system dynamics, we are using this body reference coordinate system just like I explained a few minutes back. That's what we're going to use. So we have this vector R that is describing how much the body reference coordinate system is moving with respect to global X and Y axes. And then we have this rotation matrix that is orthogonal, mathematically orthogonal, meaning that if you're going to form vectors using the columns, they're going to be perpendicular with respect to each other. That's a 90 degrees angle, as it is the case. As it is when you see me in a corridor, you say respect, like this. These fingers are in perpendicular with respect to each other. So that's a coordinate system. They're not unit in a length because the fingers are not necessarily unit in a length. So it's not the real coordinate system because in a real coordinate system, the vectors are also unit in a length. All right, so that's what we learned. We also learned about these rotations in three-dimensional space. We're going to take a look at the example because some of you were skeptical, like, I don't know, this sounds like somehow samey, or this is not the way that I would describe the kinematics because obviously one rotation axis is missing. It's not necessarily missing. So this, because remember the concept is based on three successive rotations. So the key component here is successive rotations. And that's why I can make this, using this sequence of rotations, which is a z, x, z. I can put this coordinate system any orientation I want in three-dimensional space. So I'm going to show you an example momentarily. How is it you can do the rotation around the y-axis? Because that too is possible. You know that. You look at this gyro here. You can put the gyro to any orientation in a space. No problem. That's possible. The same holds here. You can put it in any orientation in a space. But what we learned, that this concept is based on three successive rotations. And the way we can describe this in a three-dimensional space was such that we have this 3x3 rotation matrix describing each of the rotations. And now I just need to remember this first rotation is amount of psi, psi. The second one is a amount of theta. And the last one is a amount of phi, phi, phi. So psi, theta, phi. Okay, these are the amount of rotations. But really what matters is that they are successive rotations. In kinematics, successive rotations can be taken into account by multiplying rotation matrices together, each of them describing one rotation. Now, three successive rotations, I need to take these three rotation matrices and multiply them together. And this is how it looks. So this is how you can describe rotations in a three-dimensional space. How exactly? In a way that you select in these three parameters, giving them the numerical values, and substitute them to this 3x3 rotation matrix. That's how you do it. The only problem, let's say the challenge here, is that how is that you can actually define these parameters, because that's not necessarily a simple thing to do. Good news about the Euler angles, really depending how you're selecting your rotation sequence, they are still quite understandable. So they are not too difficult to understand, particularly when comparing the ones that are the rotational parameters that are having 4 rotational parameters, because human brains are not getting along well with these 4 parameters. But as promised, this is something we are not going to touch in this class. You guys can relax. All right, here's an example. So I have here a vector which is obviously the vector that is describing the x-axis. So it's going to be very, very simple case, extremely simple case, because this is a rotation axis. And amount of rotation was mentioned here too. So it was p divided by 2. All right, extremely simple. So we know that the sequence of the rotation is z, x, z. So obviously the second parameter is the one that this rotation can be described. And amount of rotation is going to be p divided by 2. So you substitute in these numerical values to your rotation matrix. And once you do the math, this is how it looks like. You know, what about if you need to do the rotation, let's say p divided by 4, which is a 45 degrees angle with respect to the vector that is this one? What axis is this? Y-axis. So how you can do this? Because the y-axis is not listed here. Remember, we have axes that such that this z, x, z. How we can make it happen? So let's take a look at this one. This picture here. So what if we're going to do the first rotation? That's the way that the x-axis is pointing in the direction of original y-axis. What about that? Okay, so it's going to be p divided by 2 as this first parameter. All right. Then I said the amount of rotation is going to be p divided by 4. All right. So the second parameter, which is a theta, is going to be p divided by 4. But that's not all needed, because we did the first rotation as a to switch the places of the angle of this axis. So we need to replace them back where they were. So I need to use the final rotation, which is this. How come I have such a hard time to remember this? P. So such the way that this rotation is compensated. How can I compensate that? Minus p divided by 2. That's your rotation. You agree? Okay, same. Again, doesn't really matter how you do the selection. You know, certain disciplines like automotive engineering, they do use a different rotation sequence. It is true that they are not using the one that I introduced here. So they're using the sequence that is, if I remember correctly, they use X, Y, Z. Okay, you can do whatever you want. And you can get the different kind of representation as your 3x3 rotation matrix. Problem always is, when you're using 3 parameters, is that it could be possible that 2 rotation axes becomes to be parallel. And then you are no longer differentiate what rotation is what. And this is something that is called gimbal locking. Gimbal locking is not like mechanical lock. It's not like a physical lock, but it's an inability to differentiate 2 rotation axes. That's what that is about. Gimbal locking. Did you guys watch this YouTube video about how it lead to dangerous situation in aerospace application, this gimbal locking? It was in a YouTube, one of the YouTube listings that I put it in my slides last week. You didn't. Anyways, you don't need it. If you are not interested about that, that's okay. But you know, this could be one way to show off your knowledge. Next time you have a student gathering, you go there and say, "Hey, have you heard about gimbal locking?" That could be a fantastic way to make a good, positive impression. You think? Or maybe not. Maybe if you feel that this is not the good way to make a positive impression, you don't need to watch that. Okay, it was just like supplementary information, a little bit extra material. Here are the tips for the weekly assignments. Be careful with the radians and gradients. So, and give me the gradients and decrease. So, this is particular when you're using trigonometric functions. Make sure that you're using them properly, because if not, your solution makes no sense, of course. And if you need help, Sturas is here to help you. So he is for you. I heard, by the way, that the first week there was a guided tutorials was super crowded. Was that correct? Did you learn about the Sura's background in that guided tutorials? The way he was in NASA when he was a real rocket scientist. Real rocket scientist. You heard all those stories. Okay, good. Good stuff. Good stuff. Okay, but ask help from Suras. Don't ask me, because I might not know the correct answer. But ask Suras. He knows. Okay. All right. And what else we learned? We learned about the velocity. Very simple thing. You take the kinematics, you do no thinking. High risk situation is that when you start doing thinking, this is what you are not allowed to do in multi-body system dynamics. Only step where you need to do the thinking is that you need to set the kinematics. Rest, you just be consistent. And you're going to learn that you're going to create the equation of motion by following the certain steps. And as soon as you're thinking that I'm clever, so I can make a shortcut, that's when things going wrong. Never ever make any kind of shortcuts. Follow the principles as they are. So that makes your life pleasant because no thinking needed. All right, velocity is clear. So it is translational velocity, angular velocity, and this is a rotation matrix that is rotated 90 degrees, and that's it. Acceleration consists of three components, which is a little bit of bad news for us because inertial forces too will be related to these three components. So what that means for us. Some of the inertial forces will be linearly related to acceleration. Here's a translational acceleration. Here's angular acceleration. But some of them will be quadratically related to velocities. Why? Because this guy here in the middle is quadratically related to velocity. So where this came from? Kinematics. We made a mind about the kinematics, and this is a consequence of that. That's what it is. All right. So then something extremely important was this constraint. The constraint makes the mechanism to move in a certain way. So like I said, they're limiting the motion possibilities. So that's where they becomes to be extremely important, like crankshaft. So if I take a hold of the piston body here, and if I move the piston body to left, the neighboring bodies, which is a connection rod and a crank itself, they have to follow the motion in a certain way. What is this certain way? This is defined by constraints, because the constraints are telling the neighboring bodies that no, you cannot move as you want, but you need to obey the motion of the piston body. That's coming because of the constraints. Though, and this, by the way, this is something that is art of motion. So if I say that this one here is have to move to this direction according to, let's say, the x equal to time, or let's say the even better sine time, then this piston goes back and forth, and the system can be analyzed using the kinematic analysis only. Why? Because this system here consists of 1 degree of freedom, meaning that the system can move in a one way only. All right, so we get back to this different kind of the definition of different joints momentarily, but this is something that is a very, very simple equation to understand. So the number of degrees of freedom can be computed once you know the number of unknowns. What are the unknowns? Those are generalized coordinates. Those defines each of the body translation and rotation. So they're telling the configuration of each of the bodies in a system. Constraints limits motion possibilities. So it's a simple math. Number of generalized coordinates minus number of constraint equation. That's going to be your number of degrees of freedom. All right. And now we can have three different scenarios. Number of degrees of freedom can be positive, more than a zero. this is something that you really need to, let's do the following. Let's breathe really deeply. One more time. Now, we can have a different scenarios depending on the degrees of freedom. And once you look at these two scenarios here, they look alike. They look that there's no difference, but there is a major difference. Major difference is that the one is kinematically driven because it's driven by motion. It's driven by driven constraint. So it's something that I'm saying that the one body have to follow the predefined motion, which can be considered and will be considered as a constraint. The one that is driven by motion is, of course, this one. How come? You know, we know that this system is a 1 degrees of freedom system. So there's 1 degrees of freedom in original configuration. And now I'm saying that actually I'm going to introduce one additional constraint. One additional constraint is going to be something that this crank body here is no longer free to move or no longer free to rotate because the rotation is only degrees of freedom. Only way it can move is no longer allowed to rotate as it wants, but it has to follow this equation, which is a constant angular velocity equation. So the body will gonna go with a constant angular velocity. So it's a predefined motion. How is that the other bodies? What they're gonna do? They're gonna follow this motion because of the constraints. Now, initially 1 degrees of freedom, but because of the driven constraint, this 0 degrees of freedom. So it's a kinematically driven system. So the response can be solved by using nothing but constraint equations. Constraint equations only. That's what it is. Okay, what about the second scenario? Now, I'm not using predefined motion, but I'm putting a moment here. How much degrees of freedom will be taken away because of the force or the moment? How much? 2, 1, 1. What about 0? What about no degrees of freedom is eliminated because of the force? Look, let me revisit in a previous slide. Here, remember the degrees of freedom is based on number of generalized coordinates, number of constraints. Is the force equal to the constraint? No, it's not. Force is a force, constraint is a constraint. So that's a different story. So the number of degrees of freedom here is going to be how much? Okay, so there's going to be, let's compute, there is a 1, 2, 3 moving bodies, so it's going to be 9 degrees of freedom, all right? Then I have here revolution, revolution, revolution. So it's going to be 2 multiplied by 3 revolutions. And then there's going to be translational joint, which is going to take 1 or will need 2 constraint equations. There's going to be 2. There's a 1 degrees of freedom system. So can it move based on the force? Yes. This is something that is conceptually very different than this one. And simply because now the response is no longer based on the constraints only, but it's based on the force. How much, I mean, the bigger force, higher responses. You understand that? How much is the response? Well, we don't know. So what we need to do is that we need to create the equations of motion and then solve these equations of motion in forward of time, which you do not know. Like, what is this equations of motion? You don't have no idea this time. But we get back to this later. Our constraint is, of course, that there's too much constraints. You're like this. The system is unable to move. It cannot move anymore. It just cannot. You understand that this mechanism is locked. That's a physically locked, like really locked. Cannot move anywhere at all. Okay. Number of degrees of freedom in a kinematically driven system is. That's my first in-class quiz, and it is on already. This is what we discussed a week ago. Remember. Okay, now I have a good vibe, very good vibe. I'm What is this smell? Is it smelling like 100%? I think it is smelling like 100%. You also smell the same thing? You don't smell it. I smell it 100% success rate here today. Yeah, it's going to be a 100% for sure. I'm too scared to say that I'm going to call to Rector if you're going to score 100% because I think you guys going to score 100% today. What do you think? For sure, for sure. Okay, let me leave this. Let me continue. Okay, these are the number of constraint equations needed for different constraint cases, joint cases. Yes, sir. Not really, because those are staticals. Those are oh, this is, by the way, the fantastic question. Fantastic question. The question is that is there any practical applications about over constrained system? Okay, yeah, there are systems that are. And this is what I wanted to show. This one here, the system that cannot move. Of course, these are something that you can find when you think about the deformable bodies. But now you need to understand that we have this assumption that the bodies are rigid. And there is no really practical application such like this. But those of you that figure out the practical applications about this case, let me know. Or maybe there is something like this. So which one? Like what? Bridges. Yeah, but then it's not the rigid body, but it's a deformable body. So of course there's this statically underdefined system. So this is something that you can find quite a bit. And today too, like you can see the cases like the door. I'm going to introduce you the door, and that theoretically is over constraint, but not necessarily if we look at this carefully, like we're going to do later today. But in a motion analysis, this because this system cannot move, and this course is about the dynamics. If there is no motion, no dynamics. That's a good point. What is this? Am I sensing also, in addition to smell of the 100% success rate, am I sensing smelling friendship? I become to be friends. You should look at your face. You're terrified. Like, oh my God, absolutely not. Everything but not friendship. We are not friends. Why not? Why we cannot be friends? Okay, forget about it. That. Okay, here are the number of constraint equations needed in the different cases. Fixed joint is not even a joint because it eliminates all possible motion scenarios. So it's not making any sense to use anything like that. Revel joint, two constraints. This is what we learned earlier. Translational joint, I'm going to show you an example later today. Two constraint equations. Primitive joint, one constraint equation only, because it only limits, as it is shown here, it limits the motion in this direction. It can still slide along this primitive axis. And this doesn't need to be a straight axis. It can be curved or whatever predefined thing you want it to do, and it can rotate. So it only takes 1 degree of freedom away. Only 1 degree of freedom. Okay, that's, if you have a crankshaft like this, revel joint, primitive joint like this. The primitive joint could be in this angle. I have two moving bodies, so I need a total of 6 degrees of, give me 6 generalized coordinates. And then I have here 1, 2, 6, then minus, 2 multiplied by 2 joint, and then one primitive joint because of this. So the degrees of freedom, 1. All right, so let's move on. What is the number of degrees of freedom? Let's compute. Let's practice this a little bit. I have here planar mechanism. One is clear, another one is not so clear to understand because this two is two cylinders, two hydraulic cylinders. So there's actually like two bodies here, that there's a revolute joint between these two bodies. There's like a piston here, piston body here, and then the cylinder here. Okay, but let's get started from this one here. How many moving bodies I have here? Let's compute the number of moving bodies. You guys want to guess? How many? 3. Okay, 1, 2, 3. If I have 3 bodies, how many generalized coordinates I need? Correct. That's going to be 9. Then only thing we need to do is that we need to compute the how many different kind of joints I have. So I have 1 translational joint. So that's going to be 2 constraint equations. And then the only thing left is to compute the number of revolute joints. Revolute joints, each of them needs 2 constraint equations. So let's compute. 1, 2, 3, 4. 4. Okay, so it's going to be 10 minus 1. What went wrong? Something is off here. Ah, this one. Is it? Ah, that's not connected. So it's not connected. So this, okay, so the problem is this. Instead of 4, this is 3. Because this is not connected. This is just a joint, but not connecting bodies. Nice. Okay, so it's going to be, now let's recompute. This is going to be then 8. 1. 1 degrees of freedom. So it can move one way only. Second one. Now, how many moving bodies I have here? 1, 2, 3, 4. How many generalized coordinates I need? 12. That is correct. 12. How many translational joints? 2. How many revolute joints? 1, 2, 3. 3. That's going to be 6. This is 4. So that's going to be 2 degrees of freedom. What is this 2 degrees of freedom? So if I extract the cylinders simultaneously, this end go down like this, and then I can extract another one and make another one to be smaller, so it moves like this. So those are the 2 ways structure can move. You got the point. You understand how to compute the degrees of freedom. You sure? Are you all doing like this? Like this? You sure? Absolutely sure about this. Okay. All right. So let's compute it then. What's going to be the number of degrees of freedom? This is a second in-class quiz, but before that, let's take a look. Let's see if we have a need to call the vector. So the first one is going to be, the first in-class quiz is going to be, you guys can see this right now, but I'm going to show it to you momentarily. Oh, we got 127 answers this week. I think it is more than usually. Yeah, you can see this here. Okay, so question is, my question to you is it or is it not? Maybe. Okay, who is voting that it's going to be 100%? You only. So it's going to be you and me against others. Seriously, guys? You don't believe this? Oh, is it? Is it? Is it? Oh my God! Yes, it is. I made it. I made it. Who can take a picture of me and 100%? Can you please? Can you please do that? Here. Is it okay? Fantastic. Fantastic. This is I'm gonna email to our rector, right? Yeah. Fantastic. This is really good. Should we call for a day? Should we leave back home? Because it would be fantastic to stop here when things are shiny and everything. Because next one I'm scared. I'm a little bit scared. Okay, I like to live dangerous. Let's make another 100%. Another one. Another 100%. Okay. How is gonna be the number of degrees of freedom in this case, which is this mechanism here? Okay, count the number of moving bodies. Count the number of revolute joints. Count the number of primitive joints and do the math. I'm going to put this back in a presentation mode, and I need to take a look at how things are in YouTube. Here, just a second. Okay, then we can come back to this in-class quiz momentarily. Okay, number of degrees of freedom is the equation is there. You guys all you saw the mechanism, or you need more time to think? Okay, I think that I'm gonna win this year. I'm gonna be the best teacher ever. I'm gonna win this university competition about, this teaching award because of my picture of with 100% success rate. Okay, are you guys ready? Or you need some more time? Okay, I'm gonna move on. Okay, can I move on? Still not. No, this is a primitive joint. This one here is a primitive joint. This one, primitive joint. So it eliminates the motion in this direction. This is the only constraint, but this is only the motion limitation it introduces. The body can still slide up and down, and it can rotate. Yeah. All right. So can we move on? A little bit on names. This is not important, but in multi-body literature, in a computational dynamic literature, there's a names, and I would like you to be aware of these names. Okay. So there are holonomic constraints, which is typically the constraints that this class is only about pretty much about holonomic constraints. Reveal joint, translational joint, conventional joints goes under the category of holonomic constraints. Non-holonomic constraints is a little bit of special case. We are not going to touch this term of the constraint in this class. They are like disk rolling in a plate or rolling in a surface, kind of the constraint. If you wanted to model the bicycle, yes, then you need this kind of the non-holonomic constraints. But if not, then you don't necessarily need this kind of the constraints. Scalenomic constraints are they're time dependent, so they are like the ones that are function of the time. So this is a one possible subcategory of the constraints, and then reonomic constraints are driven constraints. Those are the ones that we need to deal with if we're going to do the kinematic on this. Don't memorize this. This is for your information level, so not too important. But let's look at this shortly about how many constraints are needed in spatial case. All right, I realize that I keep on doing these promises and saying that we are not going to deal about three-dimensional space in this class, then we do that. Sorry about that, but soon we are not going to touch the three-dimensional cases any longer. But this is a screenshot from one of the commercial software called Atoms. How many constraints are needed for different kind of three-dimensional joints? Joints are, well, you can read it by yourself. I have here fixed joints, so it needs 3 plus 3, so it's no motion whatsoever. Translate revel joint needs 3 plus 2, so it's a 5 constraint equations. Translational joint the same, but it's different order. Cylindrical needs 2 plus 2, and so on and so forth. So this is how you can count the number of degrees of freedom. You can, in three-dimensional space, use something that is called primitive joints. And with help of the primitive joint, you can make the matrix to be completely full. And you can have any combination you want, as it is shown here. But not what you cannot do, you cannot combine the conventional joints. You can only combine the primitive joints. Okay, we learned that the revel joint needs 5 constraint equations. In the three-dimensional space, the one body needs 6 generalized coordinates. Okay, so I have here a door, the one that separates us from rest of the world. Okay, so how many bodies I have here? One body. Okay, how many generalized coordinates needed? 6. And then I have here revolute joint in the middle. Okay, so revolute joint, we learned from this slide, this table here, revolute joint needs 5 constraint equations. So that's going to be 6 minus 5, 1 degrees of freedom. But when I look at the door back there, that's not the way that it's constructed. It is constructed by 2, sometimes 3 revolute joints. Okay, so let's compute how many degrees of freedom we have in a door that is back there that separates us from the rest of the world. Okay, 6. And then I have here 1, 2 revolute joints. So it's a 5 multiplied by 2, 10, minus 4, locked. This is it. We cannot escape this place anymore. Your rest of your life, we're gonna be here because I just demonstrated the door cannot operate. Anything wrong in my demonstration? Or are we all gonna die here? Oh my God, we're all gonna die here because we just proved mathematically that we have no hope left. This becomes to be serious. They serve the same purpose. Maybe we have a hope. Maybe we have a hope here. Okay, because you know what they do. The constraints supposed to be something that are independent. They're supposed to constrain the coordinates independently. And obviously, like exactly like you said, these constraints are eliminating the same motion possibility. So they don't actually do the elimination. This is something that if you look at the lecture notes, I don't know if you guys printed out the lecture note as I instructed you to do in the very beginning. Probably you didn't. But anyways, so if you have a case like this, it's called redundant constraints. Not very serious because it's redundant. They're eliminating the same motion. And that's why commercial software, when they see this, by the way, can be considered as a modeling mistake. It's not a good modeling practice to use a redundant constraint because reaction forces becomes to be a mess. You are no longer clear what is a real reaction forces that comes out from your model. But you know, if you have 2 revolute joints, this point here, they don't actually limit the motion possibilities. Why not? Because the constraint is supposed to be independent. They are not independent because they are eliminating the very same motion possibility. This is what it's called redundant constraint. Very often asked in midterm exam, what is a redundant constraint? Good to memorize that. Okay, so let me see. So we started, was it like a 5 or, I think it was even more than 5 minutes behind the schedule. So would it be roughly the time to have a break? You need a break? No? No break? 5 minutes? So can we have a 5 minutes break? Let me just see what comes next. Yeah, this is another good example about redundant constraint, 4-bar mechanism. Good example. Let me just compute this. So moving bodies, 3-dimensional space. I have a total of 3 moving bodies, 6 generalized coordinates for each of them. So it's going to be 18 generalized coordinates. And then I have here 1, 2, 3, 4 revolute joints. So it's going to be 5 multiplied by 4. This is going to be 20. So it's minus 2 degrees of freedom because it's redundant. They eliminating the same motion possibilities. Like this revolute joint and this revolute joint, you know, they eliminate the motion in a off-plane direction. So that's why they are redundant. You can easily end up to have a redundant system, particularly in a 3-dimensional space. So the better modeling practice will be taking this away using, for example, in-plane primitive constraint instead. All right, a little bit fast. All right, more constraints is ahead of us, but let's look at the in-class quiz and then the 5 minutes break. how that sounds like. Okay, okay, don't go anywhere. So let's look at the in-class quiz. We scored. And this one. Okay, I got 123 answers. Last time it was 127. Okay, seriously, what's going to be the success rate? It's not going to be 100% anymore. Ever, never, ever in this class. I don't think so. By how much? 70, 70, 70. Yeah, I'm saying 70 percentage, right? Okay. Oh, we got more students. Oh, that what makes me very, very worried because usually these latecomers are having no ideas, like they are completely off. They have no clue. 100. Oh my God, the number is increasing. So this is a high risk game. Okay, ready? Oh, not bad, not bad, but not bad, but not 100%. Okay, remember how you did the computing. Remember how you computed. So let me just make sure we all understand this, and then we're going to have this break that I keep on promising we're going to have the break. Okay, so the mechanism was this one. Okay, let's compute this together. Ah, just a second. Here. Okay, two moving bodies, two moving bodies. Okay, fixed generalized coordinates because every body needs what? Three generalized coordinates. Correct, correct, correct. Okay, then I have here 1, 2 revolute joint, 2 multiplied by 2, and one primitive joint, plus 1, 5, 1. Okay, how things will be different. Hear me this. This is extremely important you to understand. How things will be different if my primitive joint will be such that this is my first body, second body, and the primitive joint will be this direction. How things will be different if the primitive joint is not the straight line but the curve like this. 1, still 1, because it is a primitive joint. Don't get confused about what is its direction or shape. This doesn't matter. That doesn't matter. So now, hear me this. If my next in-class quiz is this very same mechanism, but primitive joint this direction, your answer will be what? Same, but your answer will be what is same? 1, 1, 1, 1, 1. Okay, clear. 1. Because I'm going to ask this momentarily. All right, 5 minutes. Please come back. Using the door, we demonstrated that is still, we have hope. It's still going to operate. Okay. Ah, yeah, it's actually very weird that I don't see any voice going out today. Hmm, really weird. Okay, let me take a look by myself. Um, ah, it would be. Are these slides available? Yeah, of course they are. Have you guys not noticed? So it's in a modal database. Everything in a modal database. Okay, so I think it is pretty much time to go again. Let me just see if my voice is on again. Yeah, it is on. So display. All right, they're on like there. Somebody was asking if these slides is available somewhere. Yes, they are. Do you know where you can find my slides? Modal database. So in Moodle we have like a first period, and then under the first period there are week. No, it's not the week, but it's topic one, topic two, topic three, and so on and so forth. So click the topic corresponding topic, which is corresponding the weeks, and there you can find my slides. Right. Okay. Oh, not this one. I need to go like this way and this way. All right, let's practice. So what follows is that we're gonna practice a little bit about how to make constraints. And then I will introduce you one bit more complicated constraint, which is a translational joint. This is not going to be, let's say that's not really asked in a written exam. So I'm going to briefly introduce that to you. So I'm not going to emphasize that because for you it's going to be enough if you can deal with the revolute joint, the primitive joints. That's that's all pretty much needed. All right, here I have an example here. So this is a planar beam-like body, and it's constrained by using primitive joints in both ends. You see the primitive joint works in such the way that here, where the point P is located at, the motion is such that it can slide along this global x-axis direction, but it cannot move along with the global y-axis direction. This is constrained. This is not cool, not okay. Okay. Then I have another primitive joint, which is a point O here. Same story. So it's a primitive joint. This point can do everything it wants, except it cannot move along the global x coordinate axis. That's constraint. All right. How is that we can define these constraint equations needed? We already know that we need a total of 2 constraint equations. So that's how much we need. How is that we can define the constraints? By using the the kinematic equation that we are familiar with. So we're going to use this equation, the one that you might already have memorized. We're going to go to this point P, and we're going to say that, by the way, this point P is no longer able to move along the y coordinate axis. That's the plan. That's the strategy. Now let's just execute the strategy. That's it. What about this point O? It cannot move in. Yeah, same story. The strategy is this, that we're going to use this equation to go all the way to this point, and then we're going to say, hey, no longer motion in a y-axis direction is allowed. So it's prohibited. So that's the game plan. All right, let's get started from point O, the one that is located here in the lower right corner. Here's the thing. So sometimes you feel that I need to make a shortcut. I need to make my life simplified. I want to not to follow this kinematics because it's inconvenient or whatever. No, please follow the kinematics no matter what. So like we're going to do here. So we're going to first go to this origin of the body reference coordinate system using this math, this vector r. Then we're going to take the rotation of body reference coordinate system into account. And then with help of vector u bar, we're going to call the point where the constraint is located at. Okay, not complicated. Only complication, only kind of problematic part is here. How is it we can set the vector u bar? And to do that, you need to put yourself in a position of the body reference coordinate system. You need to put your angles with respect, parallel with the body reference coordinate system. And then you do the final leg, final traveling. All right, you here, your x-axis pointing downwards. So how much you need to travel along the x-axis? So it's going to be the length of the body is L. So it's going to be amount that is this much. L divided by 2. What about this direction? 0, because you're already in your final destination. So that's your vector u bar. Now comes the only difficult thing, because it says that this point here need to be from the distance d with respect to origin of the reference coordinate system. Okay, so where should I put the d? I should put the d such that the motion in x direction, because this is a motion x direction, is d, meaning that is a constant. That is a constant value d. So it cannot move anywhere else except the position d along the global x-axis direction. Okay, the rest, this can move as it wants. But this is going to give me the first constraint equation like this. So you're going to take this row multiplied by this vector. This is it. Simple. You move everything in a left side of the equation. That's your first constraint equation. Can you follow me? Can you all do like this? Yes. You understand too, or you just do like this? Both. Both. Fantastic. Really fantastic. Okay. So what about the next one? Same procedure again. Absolutely nothing but the same procedure. So we're going to go again here with help of this guy. Then we're going to take the orientation into account by using rotation matrix, account, and then vector u bar. Vector u bar. Now we are again here, x-axis pointing downwards, y-axis perpendicular direction. Okay, how much we need to travel this x-axis direction? Minus L divided by 2, minus because we're moving minus direction. How much this direction? 0. Again, now this length here is defined here, E. That's where it goes. And you do the math, that's your second constraint equation. Yes, sir. Oh, minus E. Because the E here originally is here in right side of the equation. And I said that let's move everything to left side of the equation. So when you're crossing the equal sign will be changed. Because it's like this. Ry minus L divided by 2 sine theta equal to E. And now the E goes sorry about my messy, goes this direction. So that's why the minus. Okay, fantastic. We all in the same page. Is it too simple? Too difficult? What about this? What the constraint equations are doing for you? Okay, are they defining you the center of the mass? Have we discussed about the center of the mass? Okay, they define the physical dimension of the body. Have we discussed about that? Then the last one is, this being a teacher is a lot of joy and also a lot of unhappiness. Unhappiness comes when somebody's voting this one option that makes me very, very sad. Very sad. Very sad. Okay, so the next one is where is it? This one. Okay. Now there. Circuitive is on. Oh, you can't see. Okay, yeah. Oh, now I made a mistake. So I need to do this, redo this projection thing one more time. Okay. Take a look at the options, and then what follows is we're going to take a look at how is that we can describe this uh, translational joint, and then we're going to practice one more time about crankshaft mechanism with the primitive joint, and then if we have any time left, then we're going to discuss about kinematic analysis. Okay. All right. So now what I need to do, I need to apologize. I need to put this projector off, put this in a presentation mode, and then again, like this. All right. You guys clear? All right. So we're getting back to this momentarily. But before that, let's look at the case where we have a translational joint between two bodies, beam-like body and box-like body. And then, as you already probably guessed, the box-like body can slide along the beam-like body. And to make that happen, I need to introduce this translational joint between these two bodies. Okay, these two, as promised, requires two constraint equations. One is very simple, and one is very, 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 very complicated. And if you don't understand, that's okay, because no one else is. I'm not sure if myself if I understood this well. So it's very, very complicated. So no need to get confused if this is going to be uh, something that is overly complicated. All right. First thing first. So we need to set the body reference coordinate system for both of these bodies. The beam-like body is going to be located in the center of the mass. Is this one here? So it's called body A. And the second one is a body B, like here. Okay. The first constraint equation is very, very straightforward because, because of the translational joint, these bodies have to have the same rotation parameter, theta, because they cannot move like this. That's not possible. They can be initially like this, but once this angle is set, then they must have the same rotation angle all the time. All right, so the first constraint equation is very, very simple. I just say that, the angle of the body A minus angle of the body B need to be constant. Constant here, I'm calling as a C. If it is 0, like it is a case, according to the figure here, C is equal to 0. That's your first constraint equation. Second one, more complicated because they can still slide along the beam-like body. That's still possible. How to make that to happen? All right, so we need to get a little bit of assisting coordinates here. So we need to set the two vectors here, and we're going to use a perpendicular condition, mathematical condition, excuse me, to make them to be perpendicular all the time. So first one, so we're going to set that there is a vector that is called KAB that is traveling here and ending here. So it's traveling from first body reference coordinate system ending the second body coordinate system. Q here is going to be the one that belongs to body B, and I'm going to have another vector that is called HB. I'm going to set these two vectors to be perpendicular. That's going to be my second constraint equation. All right, a little bit complicated, but let's just follow the procedure. Let's make the first vector. Okay, now you have a clear picture here. So I'm going to select in this point here, O, this point here, P, this point here, Q. Once I have these points, then I can define the vectors that are between these points, 3 points. 2 vectors, here to here, here to here. Clear? You still with me? Great. Okay, the first vector is going to be this one here to here. So I'm going to define this point O. How I'm going to make it happen? Again, the only equation that I know, I follow in my kinematics. So I'm going to take the, I'm going to go where the original body reference coordinate system is located at, here, R. Then I'm going to take orientation of the body reference coordinate system into account, and with the U bar, which happens to be 0 vector in this particular case. This point here, this point belongs to body B. Same kinematics, absolutely no difference. The same kinematics, first here, and then the vector, this one here, turned out to be 0. Okay? Then H belongs to same body. So I'm going to first go with this point where the vector U bar is going to be 0. And then the point, which is this one here, where is non-zero. Okay? Because they're in the same body. I can write it like this. Then the perpendicular condition. Remember that in mathematics, if you have two vectors perpendicular, you can have this vector transpose multiplied by vector. If this is equal to 0, this is perpendicular condition in mathematics. Let's make it happen. It's a big mess, but let's make it happen. So this is the vector H. So it's pretty straightforward. This is a vector K. And once you do this mathematical operation, then it's going to be, of course, when you're using these simplifications, then the final constraint equation look like this. Sorry, I was a little fast when I did this explanation. But just think about the concept, not so much about mathematical details, but the concept itself. Okay, like mentioned, this is for your information level. I don't expect you to master this complications, this level of difficulty. Okay, are you relieved? Good. Then this one, this mechanism, this is something that we are familiar with, remember? So this is the same mechanism we looked earlier. So it consists of two moving bodies, two revolute joint, one primitive joint. What's going to follow is that we're going to create these 5 constraint equations because it's a total of 5 constraint equations using the kinematics, the only equation that we are familiar with. And once done with that, then we're going to have a vector of constraints. Okay, first thing first. If you have a mechanism like this, what is the number of degrees of freedom? Is it smelling again? Is it smelling again? The 100%. Is it again? Is it coming again? Oh my God. 2 times in one lecture. If this is really going to happen, and look at this. It's not just that it's me and Mustafa answering these questions, but it's 130 something answers. So it's a big round. There's a lot of people here. Okay, but hey, let's look at this first. So let me take this off. Okay. All right. So hey, we have here 135 students here. What's going to be success rate about the constraint equations? 90. Okay, how many will vote this defining the particle rotation? 0. Okay, first target is this. The people out there is no one voting this D. Okay, we have a lot of good news. Look at how close we are the 100%. So it's like unbelievable, really unbelievable, because this question is difficult. Always, life is sunny days and rainy days. Rainy days at defining the particle rotation, we still have a 1%. 1%. It is not much, and it's reducing. Next time, I'm thinking it's going to be 0%. All right, good job. We're close. We're very, very close. But the next question is this. What's going to be the number of degrees of freedom? And you need to see this mechanism, this one. Count the number of bodies. Then once that's clear, then you can count the number of generalized coordinates. Once that is clear, then count how many constraint equations. And then that's it. Then you're done. Okay, let me put this back in a presentation mode like this. So I'm back in the presentation mode. Do you need more time to do your math or is it all clear? Done. You have a can-do attitude? You feel strong? Yeah, me too. Good. Good stuff. Think about what's the difference between these two mechanisms. I think what I need to do is I need to take a look at how well we scoring from this in-class quiz, because otherwise it becomes to be not so much fun. Okay, you guys ready? Dux is red. It smells so strongly, 100%. So I cannot. I'm saying that it's definitely 100%. Definitely. Okay, we still are expecting the last ones to cast a vote, not casting vote. Ah, you cannot see this. Okay, 122 students. So last time it was 130. What was it? 132 or some 30. Oh, okay, so as soon as 124. Okay, I'm not gonna do this counting because there's a delay in my YouTube streaming. But in in five, in four, three, two, one. Okay, so it's still increasing. Okay, now let's close the case. Number, of course, the correct one is three. Three. What do you say? What is the correct one? One. Ooh. Oh. Average is still fantastic. Group, should we have a hawk? Should we have a group hawk? No? No hawking. Okay, no hawking. But it still is a fantastic scoring. Really, really fantastic scoring. Maybe I'm not sure if I can mentally handle this level of success. Yeah, this is really hard. This is really hard because, I easily adapt this up nose attitude. Easily. Tomorrow, when you see me in a corridor heading to have my lunch, I'm probably going to walk like this, this moonwalking style like Michael Jackson. Still celebrating my success here in my class. What do you say about that? Not this one. Oh my God, this is annoying thing that this projector is always wanted to do like this way, and if not, it's not willing to show me nothing at all. Okay, now here we are. Here we are. All right. First one is good lesson about no shortcuts allowed. First joint is located where their body reference coordinate system, or let's say the origin of the body reference coordinate system is located too. So this is where the body reference coordinate system is located. So can you just set this point to be equal to 0? No. You first need to use this equation that we are very much familiar with. You need to travel here, origin of your body reference coordinate system. You need to take the orientation into account, then come back where you start. You must follow this procedure no matter what. I know that you have, because I'm clever, I don't need to go back and forth. Yes, you do. You need to go back and forth. There's no other way. All right. So only complicated thing is that what about the vector u bar? So you here, your x-axis pointing this direction. So to travel back where you start with, it's going to be minus. Is what? Is not in a YouTube. Huh? Is not. How come not? No, it is. So how it is displaying? Because I don't see this live. How it display? Black. Not the present days. Yeah, that's display capture. Hmm. I don't get it, this thing. Let me make another display capture here. Maybe that's gonna help us. When I disappeared, when that happened, you guys don't know it. Uh, was it long ago that I disappeared? 3 minutes ago. Really, very unfortunate. Okay, can they see it now? They should be able to see it now. Okay, yeah, it's coming back. This is a weird thing, never happened before. Usually this OBS is very solid, very, very stable software because all other, me and other YouTubers are using it. So it's not just me, but the entire YouTube community is using it. Okay, is it, okay, is that a problem? Are they saying that I'm relieved? If they say that, I can imagine, I understand that they are relieved. Order top. Okay, what about now? I think that I'm there. Yeah, it always comes with a little bit of delay. So I think that I'm gonna be there. Today having is a little bit of bad day regarding the technology. Okay, so it's okay. Yeah, I'm there too. I actually should have like one of these small monitors here to see how I look like. But then it would be all the time me like this, not focusing on the teaching anymore. But here's the thing. So this is what we did. So we use this equation, the only one we are familiar with, this one. And we went here and we came back. We came back by setting the vector u bar such that the x-axis is minus L divided by 2. Because we here, an x-axis pointing downwards. We don't need to move the y-axis at all. Now we need to set this to be equal to 0 because where the revolute joint is located with respect to global coordinate system, its origin. So that's why these two parameters need to be 0. This is going to be your two constraint equations. Next one. This is something that we know already. So we are familiar with this concept. So we are setting the revolute joint that connects the body A and B. How? Using the kinematics. So setting these kinematics to be equal in this particular point, that's going to be your second set of constraint equations. Second set, as this is going to introduce two constraint equations. Okay, we're going to go first, origin of the body reference coordinate system. We're going to take the orientation into account. And then, because x-axis is pointing in this direction, we need to travel L divided by 2. Transverse direction, 0. That needs to be equal than the very same point, but using body B. Okay, here. We go here with help of this guy here. We take the body orientation into account, and then we travel backwards. Minus L divided by 2, 0. You move everything to left side of the equation. That's your second set of equations. Clear. Final one. This one here cannot move along the global y-axis direction. So this is where the point is located at. So you're going to go first here, this guy, then orientation, this one here, and then you're going to go here. This is going to be your vector u bar. And then you say that, okay, this guy here, this one, need to be equal to 0 because it cannot move global y direction. So you take this component, this row, multiply by this. That's your fifth constraint equations. Okay, let's open this because I would like to put this like something that you can think about it during the week, and then we get back to this next week, Monday. If I do the math correctly, we still have like 3 minutes left, do we? Because of the 5 minutes break or something like that. 14, but because it's a 2 times 45 minutes. So I'm going to open this. We can take a look at the concept of the Jacobian matrix. And then once this concept is clear, then you're off the hook. How about that? You're looking forward to be off the hook. Okay. Jacobian matrix, kinematic analysis. Okay. So this whole story is related to kinematics. All right. Kinematic analysis is actually used quite a bit. So if you look at the CAD software, and there's like collision analysis that figures out if there's assemblies possible, this kind of the stuff is typically made by using kinematic analysis. Kinematic analysis is an art of motion. It's not about the forces. We discussed this earlier. So the forces are off the plate, off the game when we have the kinematic analysis. As the post-processing procedure, you can, if you are really interested, you can figure out the forces too. But as a analysis type, is only about motion, position, velocity, acceleration, levels. That's what it's about. And you know that you can conduct the kinematic analysis if and only if the number of degrees of freedom is 0. Oh, this is, by the way, almost like in this. Well, you guys have probably never been in this rock concert, but in a rock concert, sometimes the singer is not singing but giving the mic to the audience, and they are continuing about that. So it's like almost like that when I'm saying number of degrees of freedom is, you say 0. Nice. Okay. Now, these different levels are really, really different depending what you're aiming to do. So if you wanted to get this position analysis, that's hard. That's not easy. It's based on iterative process because we do have equal number of equations and unknowns. Those are matching numbers, but those are nonlinear algebraic equations where the unknowns are hidden inside of the equations. So it's not simple to solve these kind of the equations because they are not explicitly expressed, but they're hidden inside. So you need to use numerical techniques to solve these positional level equations. But the solution is hidden in constraint equations. Velocity is the simplest. It's a matter of simple substitution. So it's very, very simple to solve the velocity once you know the position. Acceleration is okay. It's also a matter of substitution. It's not as simple as the substitution in a velocity level, but it's doable. Once you have the constraint, rest is mechanical, rest is a polar plate. So it's downhill. The most challenging thing is a constraints. Constraints, rest is mechanical. Okay. And we already know how to do the constraints, so we are okay. So not a big problem. But the kind of the challenge is this, when you make a vector of the constraint equations, so the length of the vector is matching with the length of the unknowns. The length of the vector is same that the length of the generalized coordinates. So we can solve the generalized coordinates. The problem is this: the generalized coordinates are hidden inside of the constraint equations. So they are not explicitly mentioned. How you can solve this kind of the nonlinear equation numerically? This is something that I'm sure you guys are aware of this thing. You have heard about this already. Probably not in a in a preschool, but in a high school perhaps. In your pastoral level studies, you have learned about how to solve the set of nonlinear algebraic equations numerically. And the method you can use that is an iterative approach like Newton-Raphson approach. Newton-Raphson, so your middle name is a Newton-Raphson, so you know this back and forth. There are no surprises. Okay, we can use a Newton-Raphson approach. A Newton-Raphson approach is something that we need Jacobian matrix. This is how the Newton-Raphson goes. Of course, I should give it a solid, waterproof explanation how this came up with. But as cutting the corners, it goes in such a way that if this is your set of nonlinear equations, what you should do when you wanted to solve this equation using Newton-Raphson approach is that you compute the matrix where you're differentiating all these equations with respect to all your unknowns. What are the unknowns? Generalized coordinates. Then you have here delta Q, which is not the solution, but is like a GPS system. It's giving you the direction where to go to reach the final destination. It is giving you instructions how to update your generalized coordinates to get closer to solution, but it's not necessarily your final destination yet, but it's one step closer to it. You make another step, you're updating these components, you're getting closer and closer and closer until you're happy with, until you're very near to your final destination. What's this? This is minus constraint equation. And those of you that are interested, I guess that none. Still, I'm going to say this to you, that how this actually goes. You need to introduce this small displacement adding to your constraint equation, delta, this one. And then you're going to follow something that is called Taylor series. And once you do the Taylor series, you can rewrite this equation as this kind of the series. We are not going to take each of these, all these components into account because this continues forever, which says, okay, first one and the second, that's enough of me. Rest, I don't care. I simply don't care. I'm going to say, forget about it. Go home. Go back home. And then I'm going to set this equation to be 0 as it is mentioned here. And this is where this Newton difference is coming from. That's what you need to do. This guy here in the middle is a Jacobian matrix. It's a very, very mechanical thing. So you're going to take each of these constraint equations and differentiate those with respect to each of your variables. Very, very handy to solve by using a symbolic math tool. Very complicated, big pain to solve by using pen and paper. Don't use a pen and paper. Use a symbolic math tools because each of them have this Jacobian directly implemented. You just say Jacobian, you're telling this vector, this is it. So it's simple like that. Here in the lecture, we're going to do this using pen and paper just a couple of times, that just demonstrating how painful it is, how much it hurts physically to do it. Okay, but that story going to be next week. So this is how the Jacobian matrix look like. So it's nothing but the partial operation. You take your first constraint equation, you differentiate that with respect to first generalized coordinates, then with respect to second, then all the way with respect to the last one. Then you take a second constraint equation and you redo it. You will get the matrix, which is square in size. So equal number of rows and columns. Why? Because equal number of equations and unknowns. That's where the skewer shape is coming from. And then you can start solving your Jacobian. So if I look at this, remember this was what we learned a little while ago. These are the two constraint equations we look. Now you can get the Jacobian taking one at the time and differentiating those with respect to your generalized coordinates. Now one moving body, how many generalized coordinates? 3, because every body needs 3 generalized coordinates. What are these generalized coordinates? Rx, Ry, angle theta. This is where we're going to continue. Are you still coming back? But can you feel it? Can you feel that? Because what's going to happen is that you see that, if this is a time here, this is a LD, level of difficulty. We started like this. It was like singing and dancing, and then became this class. We're going up here. You feel it already. What's going to happen later is like this. Yeah. Not next week, but week after that. Okay, guys, take it easy and see you on Monday, next week, Monday.